Audio Jungle.
Hello everybody. Today we are going to talk about tax evasion, which is our topic, the first topic in our interdisciplinary studies lecture series. And I will explain the topic of tax evasion from an economics perspective. My name is Bodo Herzog. Well, on the following outline you can see the structure of my talk over the next 45 minutes. First of all, I will introduce you to the topic of tax evasion. So what is tax evasion about? Then I will introduce a model how an economist would study and approach and analyze this problem. And then we will use this model and discuss some interesting examples. And finally, I will conclude and give you some recommendations we developed during this talk. So let's start with the introduction. Well, tax evasion is a current problem. It's a problem in almost all countries. You can see this problem if you look to households, to individuals, but also to corporations. There are a couple of interesting examples of tax evasion. For instance, a famous and well-known football manager of the FC Bayern Munich, he evaded taxes approximately around 28 million euros. But there are also good examples if you look to corporations. For instance, UBS, a Swiss bank, confessed that they helped people to evade taxes, and then they had to pay in 2009 around 780 million US dollars. So you can see tax evasion is a common problem. But we have to distinguish tax evasion and tax avoidance. Tax evasion is illegal. Tax avoidance is legal. So tax avoidance somehow is a smart way to reorganize economic activity to lower the tax burden. But we are talking about tax evasion and not tax avoidance. Well, obviously it's difficult to estimate tax evasion because there is no official statistics about the level and the degree and the amount of tax evasion. It's like measuring other illegal activities like drug consumption, the hidden economy, or smuggling. Despite the problems, economists try to estimate the level and the amount of tax evasion. For instance, Ray in 1965 estimated that the tax evasion of the Italian general sales tax was around 50%, which is obviously a huge amount. And other economists like Gutmann and Feige, they also estimated the value of the hidden economy, and they came up with estimates around 10% of the gross national product, GNP, which is also definitely a huge amount. So you can see that tax evasion or the hidden economy is a sizable part of our economies today. So let me talk about tax evasion in more general. Well, from an economic perspective, tax evasion is a choice or a decision-making problem. So it's a problem that you have to decide, should I evade taxes or not? So it's a choice problem. One, A or B. But it is a problem under uncertainty because you don't know whether you are caught in the end, so that it's detected that you did it, or that it works well for you. So in the end, from an economic perspective, tax evasion is a choice problem, a decision-making problem under uncertainty. And that is the way we, economists, try to approach the problem of tax evasion and study this problem. By the way, this is a field, what we call public economics. In public economics, we study the tax system and problems like tax evasion. And now I'm going to introduce the model, and the model is by Yizaki, 1974. There are other models also by Ellingham and Sandham or Srinivasan. All these papers were published in the Journal of Public Economics. So let me talk about the model. First of all, I have to tell you a little bit about the letters, the variables, and the terminology we will need. The capital M, as you can see from the slide, is the exogenous income. That is the true income you receive. The capital X, that is the income you declare to the tax authority. And obviously, if you evade taxes, then you declare, the income you declare, the X, is smaller than the true income, the capital M. Then we have a probability, which I indicate by P. The probability describes whether the tax evasion is detected or not. Then we have the tax rate you have to pay on your declared income, X, and we capture this by a small t. And finally, if the tax evasion is detected, so you are caught in the end, then you have to pay a fine, a sanction, a payment. And this is indicated by F, capital F, and F is greater than 1. So now we study this problem in a model. And as I told you, what we have to do from an economic perspective, we try to maximize our utility, that we are happy in the end, but we have to take into account what is the optimal level of the declared income, the X, under uncertainty that it's detected or not. So now you can see the slides with the function and with the derivatives. And now let me develop every function step by step, and then you can see that what looks very complex in the beginning is possible and easy to understand. So let me start with the function we are going to study. First of all, what we do, as I already said, we maximize our expected utility function. And the utility function U is dependent on X. X is the income you declare. And usually, as I told you, if you evade taxes, the declared income X is less than the true income. So how does this function look like? Well, it consists of two components. The first component is the following. Suppose the tax evasion is not detected. Then this is described by the probability 1 minus P. And then you have the utility, and the utility consists of two components. Well, it's the true income, capital M, minus the tax you have to pay, T times X, on the declared income. So the true income minus the tax you pay on the declared income, that is the remaining income you have in your pocket, and that gives you utility, happiness, somehow. This is what happens if the tax evasion is not detected. But with the probability P, I already told you, the tax authority finds out that you evade taxes. And then the utility function looks differently. Well, in this case, it's once again the true income minus the tax you have paid on the declared income. However, we also have to subtract, because now it's detected that you did tax evasion, you have to pay a fine, and therefore we have to subtract the punishment. How does the fine look like? Well, there is this F, the fine, plus the tax you have to pay on the evaded income, which is M minus X. So take a look for a second to this third component. The third component describes the punishment because the tax authority detected with a probability P that you did it. And the punishment you have to pay is the difference on the true income and the evaded income. And on this income difference, you have to pay a fine plus, obviously, the tax you have not paid in the beginning. So this is how the function looks like, and an economist would now maximize this function in respect of X, the declared income, to find out what is for me as a household, as an individual, the best income I should declare to my tax authority to maximize this utility function, given that there are two different probabilities. P, tax evasion is detected and I'm caught. 1 minus P, it's not detected. I did it, but no one have seen what I did. If we have a function, and if we are looking for a maximum, then maybe you have learned in your business mathematics class, well, what you have to do is to compute the first order derivative, or the first order condition. And that is what we have to do here as well. So let me compute in the next step the first order condition. That's the first derivative of this expected utility function. Okay, so the first derivative is the d of my expected utility function in respect of x. So let me do this one step by step. First of all, we see this is independent of x, therefore it remains. Then we see, well, here the utility function is dependent on x. So we have to compute here the derivative u prime of my utility function. And by the way, to simplify the further writing here, let me introduce a shortcut for the term here in the bracket. Let's call this is my variable y, or the income y. And for the income component here, let me introduce that this income is described by the variable z. So back on my first derivative, we have the first derivative of the utility function, which is indicated by this prime of my income y. And then we have to apply the chain rule. So we have to compute the derivative of what is inside my utility function in respect of x. So the derivative in respect of x is 1. So what remains is the minus t. So it's times minus t. Now we continue. Plus probability p. Once again, first derivative of the overall utility function, u prime of z. And then we have to compute once again the derivative inside of my utility function in respect of x. So what is that? Well, the derivative of this in respect of x, x is then 1. So what remains is minus t. And then we have an x here as well. So this is minus and minus, which is plus in the end, f times t. And the derivative of x, if I multiply this inside the brackets, it's 1. So it is this term. And that should be equal to 0. This is now the first order condition in respect of x of my expected utility function. For further computation, I will just simplify this function a little bit. Well, what we see immediately here, that we have the tax rate t in the first term, and there is the t in the second term. So if we factor out this t outside of the brackets, we can cancel t in the first term and the second term. So in the end, the t here and the t here, which then remains just the 1, and here can be cancelled. And t is positive, so that is possible to do. And then I can rewrite this first order condition in a simpler way, which is the same as the condition on my slide. It's 1 minus p, the probability, u prime, the first derivative of the utility function. And then we have this minus here, so take care. Plus, then this p, u prime, the first derivative of the utility function, and then we have this term in the bracket, which is, I just switch the order, f minus 1 equal to 0. This is the first order condition of my expected utility function, and later on, in the next step, I will need this condition. But you may ask, well, is this really a maximum? what we computed here. To verify that this is a maximum, we have to take a look to the second order condition. And from your business or your mathematics class, you know a maximum requires that the second order derivative, the second order condition is negative. It's less than 0. So let's verify this for our function, that we have here a maximum. To do this, well, we compute the second derivative of the expected utility function in respect of x. And if this is negative, what we compute now, then we can say for sure it's a maximum. We have find the maximum of our function. Okay, here's the first derivative, and now we compute once again the derivative in respect of s to obtain the second derivative. So let's do this. Well, we see immediately this is 1 minus p. Then we need the second derivative, so we have to derive this utility function twice. Then it's 2 prime of y. And once again, we have to do the inner derivative of y in respect of x. It's this here. It's minus t again. Then we do this for the second part, which is the probability p. The second derivative u double prime of z times this term we have here. And because we have to do it once again, second derivative, this is then squared. And we have then a t, which is here outside of the bracket. Okay, so this is the second order derivative. Just requires that you know the law how to derive a function. And now let's take a look to the sign of this equation. Well, the tax rate is positive. Everyone has to pay a certain proportion. If we have a f is greater than 1 per assumption, that is what I told you when we talked about the variable, and it's squared, so it's anyway positive. The probability p that tax evasion is detected is positive as well. There is some probability. So the question is to make clear whether this is positive or negative, this second term, we have to think about how does the second derivative of my utility function looks like, and whether this is positive or negative. Well, in economics, we always assume that the utility function is concave. Maybe I can draw a graph to explain this. So if we have the income x, and this is my function u of x, then a concave function looks like this. And actually, now you can see the point. If I have 100 euros income, let's call it 1 unit, then I have a positive utility from this, let's say 1 unit happiness. If I have 2 units of income, 2, well, you see, your income level is higher than before. However, the additional contribution of a second unit of income gives you not twice happiness back. So the 2 is here. So the additional contribution is maybe then 1.5 or something like that. So what can we see from this function? It's a very important property. The first order condition, so the first derivative of the utility function, is the slope. And this slope is positive. So in other words, u prime of x, which is the slope of this tangent line, is positive. But the second derivative, u prime double prime of x, is negative. Where can I see this? Well, if you take a look now to the tangent line in the second point here, you see the slope of this line is smaller. It's declining. The greater the income, the smaller is the slope or the tangent line on this utility function. And that implies that the second derivative of my utility function is negative. It's declining. Now take a look to this second term. We have plus times minus times plus times plus. So the overall sign of this is negative, definitely. Now we have just to see what is in the beginning here. Well, the probability is once again positive. The second derivative of my utility function, as I already explained here, is negative. The tax rate is positive. And then we have a minus sign here and a minus sign in front that is compensating each other. So minus and minus is plus. So what we have here in total is then plus times plus is negative. A negative number, minus 5, plus a negative number gives definitely a negative term. So what I have showed here is that the second derivative of my utility function is negative. And this is the necessary condition that we have a maximum. In business mathematics, you have learned if the second order condition of my function is negative, then we have a maximum. And that is what we got. And second order condition is negative. That implies we have a maximum. Well, for the further computations, let me introduce a new letter and call it S. And S is actually negative, and it's the description of the second order condition. Now you can take a look on my slides back, and you see again on the top of the slide the utility function, and then you see the definitions of my variables, the y and the z, and you see the first order condition and the second order condition. We have computed step by step on the blackboard. Now you know how the model works, and now we continue to discuss the model. Now we continue with the discussion of the model. And you can see from this following slide that what we are going to do is comparative static. This is an expression and a technique we usually apply in economics. So here we study now what is the impact on one variable in my model, for instance the fine you have to pay if tax evasion is detected, on my other variable, the declared income x. And we want to learn a little bit what happens with my declared income if I change the fine, if I change the probability that tax evasion is detected. So this is called comparative static. So let me study these cases. Once again, you can see the final solution already on the slide, but I will derive and show you step by step how you can obtain this equation. So what we need, we just have to keep in mind the first order condition from our previous discussion. And then we study the first case. Let's call it case 1. And we are interested in the impact of the probability P that tax evasion is detected, that the tax authority sees what you are doing, on the impact of P on my declared income X. So I want to know what is the relationship if the tax authority increases the probability that it detects what you do. Well, you would say if the tax authority improves and is better to find out what you are doing, you would declare a higher income. You evade less taxes because it's more likely that you are caught up if P, the probability, is higher. So this is the intuitive view. Let's see whether this is also what we find in our model. Okay, now we are ready to compute the total differential in this case 1 scenario. So take a look to the first order condition, and now we compute first the derivative, the total derivative in respect of P, and then the total derivative in respect of X. So what is the derivative of the first order condition in respect of P? Well, we see immediately there's a P in front in the first term, and there's a minus and a minus, which is then a plus, and the derivative of P is 1 times the utility function u prime of y. So this is the derivative of the first term in respect of P. And from the second term, once again, we see there is a probability, p. So the derivative in respect of p, the derivative of p is 1 times what we have in the first order condition, f minus 1 times the first derivative of my utility function u prime of that. This is the total derivative of the first order condition in respect of my probability p. And now we have to add the derivative in respect of my variable x, my second variable. But now keep in mind, if I compute the derivative of the first order condition in respect of my variable x again, this is the second order derivative. What we computed on the previous slide as well. So the second derivative of my x is the capital S I introduced earlier. So this is the second derivative in respect of my variable dx. And that should be equal to 0. Now let me rearrange. Let me write down this equation in a beautiful way that everyone can see what is going on. First of all, I bring this term on the right-hand side. And I keep this on the left-hand side. So on the left-hand side, then we have s times dx is equal to, then this term on the other side, then we have a minus, and then I just copy what we have here, u prime of y plus f minus 1 times u prime of z dp. Simple algebra, nothing special. In the next step, I just write down it, and that is my last step, by the way. I write down the dp, which is here on the left-hand side, on the right-hand side. I bring it here down to the left-hand side, and I bring the s on the right-hand side. So in other words, I have the dx, and then the dp on this side is equal to, we have this minus here, and then we have a fraction in the denominator. I have then the s, and in the numerator I have the remaining term, which is here in brackets, u prime of y plus f minus 1 times u prime of z. So that's it. And this is the same term you can see on my slides. Well, let's take a closer look to this. There's something really interesting in it. And to see this, we have to study, once again, the signs of the different terms here on this side. The s is the second derivative of my function. And I have already shown you the s is negative. This is necessary for a maximum. That's a negative number. You can say it's like a minus 5 or something like that. We also know that f is per definition greater than 1, and therefore, if we have f minus 1, well, this is bigger because f is maybe 2. Yeah? 2 minus 1 is 1. So this is always a positive number. And then we talked already about the derivatives of my utility function. The first derivative is what we call the marginal utility. The higher my income, the higher is my utility, the higher is my happiness. Yeah? So this is also positive, first derivatives. So what we have, in other words, is a positive number here divided by a negative number gives a negative number. Taking into account the negative sign in the beginning gives me something positive in the end. So this term is definitely greater than 0. Positive divided by negative is negative. With the negative sign gives me something positive. This is greater than 0. What can we learn now from this finding? Well, suppose the p, the probability that tax evasion is detected, increases. Then the positive sign shows you that if p is higher, the x will increase as well. And the x is my declared income. So I will declare an income which is closer to my true income, my M, because it's more likely that what I did, my tax evasion, will be detected. So the higher the probability, the better the tax authority, the higher is my declared income. So my X will be very close to my true income M. Makes sense, and it is actually what I told you in the beginning, it's our intuition. Now let's study a second case. And in the second case, we will study what is going on if we change the fine you have to pay in case of tax evasion. Okay, let's study the second case. So the case 2, in case 2 we study the impact of my fine, my sanction, my punishment I have to pay on my declared income X. So what is the relationship between the fine in case the tax detection, the tax evasion is detected on my declared income? What would you say intuitively to this problem? Well, the more I have to pay in the end, the higher should be my declared income, the less tax I evade, obviously. Let's see whether this turns out. It follows the same procedure, and it's a good practice to do it again, what we did in the first case. So to analyze this problem, we use the first order condition from our model, and then we compute the total derivative of the first order condition, first in respect of f, and then in respect of x. Then we rearrange this, and then we find the solution. The solution is already on my slide, but I will show you in the next 3-4 minutes, once again, the explicit steps how to obtain this final condition. Well, let's now compute the total differential in case 2. First, we compute the total derivative of my function in respect of f. If we take a look to the first term of the first order condition, we see this term is not dependent on f. There is no f. And therefore the derivative of this term is 0. If we look to the second term of the first order condition, well, we see here's an f, and we know that my variable set, which was this long term in my utility function, here is also an f inside this utility function. So what we have here, we have a product. The f is here, and the f is inside my utility function. So if we compute the derivative of a product, it's the rule we have to use is the product rule. And the product rule works as follows. First, we keep the first term as given and compute the derivative of the second term. Plus, we compute the derivative of the first term, and we keep the second term as given. And that is what I'm now doing. Okay, compute the derivative in respect of f. First, we keep this term as given, which is p times f minus 1. And we compute the derivative of my utility function in respect of f. This is first u double prime of set. And then we have to compute the derivative, chain rule, of my set in respect of f, which is minus t m minus x. Well, to see this, you just have to keep in mind the definition of set, which I showed you on the previous slide. Yeah? And set contains a term which is minus f t m times m minus x. And if we compute the derivative in respect of f, then the f is 1. So what remains is this term. It's just minus times m minus x. So this is the first derivative in respect of f. And then we have to add plus. Now we keep the utility as given, and we compute the derivative in respect of f. Well, this is then p times 1, because the derivative of f is 1. So we have a p then here, times, this remains constant, that is the product rule, u prime of z. Well, this is a little bit complex, but definitely it just requires the laws of how to compute derivatives. The whole term is now the derivative in respect of f. And then we continue and we compute the derivative in respect of x, which is, once again, we use the first order condition, we compute it in respect of x, that's the second order condition. So it's s dx, and that should be equal to 0. And now the final step is, once again, to see the equation I have on my slides. We rearrange this equation. We bring the first term to the right-hand side, and then we divide by df. And with some experience, you can do this, all the steps in your head. And you see what we then have is on the left-hand side, dx equals df. And then we have here our fraction. If we move this on the other side, there is a minus then. Then we have this here in the numerator, so it's p times f minus 1 u double prime of z, and then we have brackets minus t m minus x, and then we have this term plus p times u prime of z, close the bracket, and in the denominator we have the s. Again, take a look to the sign. What is the sign of the term here, this very complex fraction on the right-hand side? Well, we know the second derivative, which is indicated by s as a short. This is negative. We know that the probability is always a positive number. My fine, which is greater than 1, minus 1, is always positive. We know that the second derivative of my utility function is negative. It's a law of diminishing utility. You have learned maybe in a microeconomics class. M minus x, this is my true income minus my declared income. Well, if I evade taxes, my true income is higher. I declare a lower income, x. So this is positive as well. The tax is positive, but here's the minus. So we have to keep in mind this minus. So what do we have? Plus times plus is plus, times a minus is negative, minus. Yeah, so it keeps minus, but now we have to take into account this minus. Well, that is in the sum. If we take into account all the signs, it is plus. Yeah? It's a negative number, but a negative number with this minus switches to a positive one. Probability is positive. The marginal utility is positive. So the second term is positive. So what we have here in the numerator is a positive number. Plus times a positive number is something positive. We divide this with a negative number. That gives me something negative. But then we have to come back to the minus. That gives me, in the end, a positive number here. So this term is definitely greater than 0. There's no doubt about that. What can we learn from this? Suppose the tax authority or the government increase the punishment, the fine you have to pay on the evaded taxes. So if there is an increase in the fine, instead of 1 million, you have to pay now 100 million. Well, this is then telling you, due to the positive relationship, the higher, the larger the fine, the greater will be my x, my declared income. Makes sense. If I have to pay more, if I evade taxes, well, then I declare a higher income, which is very close to my capital M. Yeah? Usually, x, my declared income, is not the true income. I evade taxes. But if I have to pay a large fine because I did it and the tax authority is detecting it, well, then my declared income is very close to my true income. So the higher the fine, the greater will be, the larger will be the declared income closer to my true income. That is what this equation is telling us. So now what can we learn from these two cases? First of all, we see the higher the probability that tax evasion is detected, the higher is my declared income, the less I evade taxes. And the same happens for my second case. The higher the fine I have to pay on the evaded taxes, the more I will declare, the higher is my declared income and the lower is the evaded taxes. From an economic point of view is now the following, or the question is the following. What should I do as a government? Should I increase the probability? If I increase the probability that of tax detection, that I'm caught, well, that will reduce tax evasion, definitely. Or should I increase the fine a household or an individual has to pay? That will also reduce my tax evasion. So both instruments, the probability P and the fine F, will reduce or mitigate tax evasion. But one of these instruments is more efficient from an economic perspective. Why? Well, if you increase the probability, then that means you need more people in the tax authorities that look to the books, and then they detect that you did it or you don't. So that requires the government has to spend more money for people, for experts in this field. Compare this policy with an increase in the fine you have to pay. Well, this requires no more human resources. You just announce, well, if this is detected what you did, if tax evasion is really fined and someone detects this, then you have to pay a very large fine. And that reduces the incentive to do. But from a government perspective, a higher fine is cheaper because it does not cost any resources like people. And actually, if you look to real policy, what Germany did recently, due to the cases of tax evasion detected in the previous years, well, they increased the fine you have to pay in case of tax evasion. They are not hiring more people, which means a higher probability that it's detected. It's not an increase in P. What they did in praxis, well, they increased the fine. And this is, from an economic perspective, based on this very simple model, also the conclusion you came up. It's less costly from an economic perspective to increase a fine, but it has the same impact in the end on tax evasion. It will reduce or eliminate, in the best case, tax evasion. So you can see that this model also provides you interesting insights from a policy economic perspective. Now let me continue with a second view on this problem in our last policy discussion, and then we come to the conclusions. So before we conclude, let me take a look to the problem from the tax authority perspective. So what is the government thinking about this problem? And on the next slide you can see actually what the government is looking at. Well, the government is looking at the tax revenues, and let me call this R. And what are the revenues the government obtains? Well, first of all, the government gets the tax you have paid on the declared income, T times X. And then the government also obtains, on top of this, if tax evasion is detected with probability P, it obtains the punishment. And what is the punishment? Well, it's this F times the tax you have to pay on the non-declared income, on this difference. True income minus declared income. So you have not paid taxes on this, and if it's detected that you did it, well, then you have to pay a tax on this non-declared income plus the punishment F. This is the tax revenue the government obtains. And now the government also would ask, well, what happens with my revenues if I change the probability P? Yeah, if I hire more people to detect tax evasion. And the government would also ask the question, what happens with my tax revenues R if I increase the fine people have to pay if they evade taxes? Well, to study once again this problem, we just compute the first derivatives. And then we can see what happens with my tax revenue. You can see the final results on my slide. Again, I will do here this also on the blackboard. So we compute the derivative, and it's now the partial derivative because it's a function of many variables of my tax revenue function in respect, well, let's start with probability P. So we compute the derivative of the revenue function, the tax revenue function, in respect of P. The first component, you would say, well, the first component is not dependent on P. There is no P here. Well, it's not explicit. But consider, we know from our previous discussion that my X, my declared income, is dependent on P. That was my first case I discussed with you a couple of minutes ago. So actually, it is the P, the X is a function of P. And therefore, if we compute the derivative in respect of P, we have to consider this. And therefore, it is T times the derivative of X in respect of P. This is what we computed in the previous step. Then we go on, plus. Well, here it's the same. We have a P here, and we have an X here. And once again, the X is a function of P. And there are products, and therefore we have to use the product rule. How does the product rule work? Well, compute the derivative in respect of this one, and keep the other term. Derivative of P is 1, and we keep what is here. So that's F times T M minus X. And then we keep the P, and we compute the derivative in respect of X. There's a minus, we keep the P, we keep the F, we keep the T, and we compute the derivative in respect of X, which is dx dp. Well, so far you cannot really see what is the sign, whether it's positive or negative. But if we rearrange and bring the terms a little bit together, in the next line, we can see what happens. Well, the first term is so far, we have a dx dp here and here. And in both terms, we have a t. So we factor out this t, and we factor out dx dp. Then we have here 1 minus pf times dx dp. Yeah? So I just bring together these two terms, and I factor out the t, that's a common factor, and I factor out this fraction. And then what remains inside is the minus pf, and here's just 1. So if I multiply the terms into the brackets, you see we have this term minus this term. And then what remains is plus f times t times m minus x. So take a look to this equation. Well, the fine and the tax rate is positive, and my true income is usually greater than my declared income. So this term here is positive. The tax rate we have to pay, well, that's positive definitely. And the term dx dp, this is what we already studied in the previous step. And we find that this derivative is positive. The higher the probability that tax evasion is detected, the higher, the greater is my declared income. So this is what we already studied. It's positive. So to have a positive sign here in the end, yeah, that means the higher the probability, the more is my tax revenue. That requires positive, that this whole term is positive. But if I want to have that this whole term is also positive, we have to assume that what is in the bracket here is greater than 0. So in other words, it is required that 1 minus p times f is greater or equal to 0. And I can write down this condition, if I bring this on the other side, that 1 is greater or equal p times f. Well, the p is the probability that tax evasion is detected, and f is the fine I have to pay. I know already that f, that is per assumption, per definition, is greater than 1. So if f is greater than 1, then p, that this product is less than 1, should be very small. P, the probability that tax evasion is detected, should be very small. And then this condition is fulfilled. Then this is positive. And then it happens that this condition is positive as well. And that implies the greater my probability, the greater will be the tax revenue. So to have a positive connection between the probability of tax that the tax evasion is detected and that my revenue, my tax revenues, are also increasing, requires this condition. This is what we call a necessary condition in this model. If this condition is not fulfilled, the model does not work. In a second step, I will compute now the revenue, the derivative of my revenue in respect of f. And actually, I will not do this explicitly. You can just take a look to my slide. And that is the condition on the bottom of my slide. And you can show, similarly to what we did here, that there is a positive relationship. The larger my fine I have to pay, the larger are the tax revenues. Makes sense, right? If I have to pay more, if tax evasion is detected, then the government gets more money. And that is actually what this condition is telling you. So let me now sum up and tell you what are the policy implications of the overall discussion. Policy recommendations. According to this simple model, we can see there are two instruments to reduce or to mitigate tax evasion. One instrument is the probability that tax evasion is detected, that you are caught, this probability. The higher the probability, the lower will be tax evasion. Another instrument is the fine you have to pay. And the higher the fine you have to pay on the evaded taxes, the lower will be the tax evasion right in the beginning. So both instruments, the probability P and the fine F, are substitutes. The higher the probability, the higher the fine, the lower will be tax evasion. So the government can choose both. But as I told you already, for the government it's better to increase the fine because the fine does not cost any money. It just frightens you right from the beginning to evade taxes because you know, if I do it, I have to pay a large punishment fine on my evaded taxes. It's like a death sentence. And therefore, the government, from an efficient point of view, would increase the fine to a very large number and keep the probability P at relatively low numbers. And that is what we can see almost in all industrialized countries. There is a number of people in the tax authorities who look to the books that they define the probability of tax detection, But governments try to frighten you to do tax evasion by increasing or having very high fines on tax evasion. Now you may ask, is this implication also true in a complex economy? And is this also true for corporations? And here I have to say, well, maybe not. If we look to corporations, the topic is even more complex than the topic we have studied in this simple model. And I give you 3 points why this is more complex. First of all, corporations, they have better possibilities also to avoid taxes, not to evade, avoid taxes, by shifting the profits to different countries with different tax rates. They can also maybe make a mistake in the reporting process, which is not counted like tax evasion. There's a second problem when we look to corporations. If a corporation know that, well, in the end I have to pay, if my tax evasion is detected, a very high punishment fine, then the corporation would say, right in the beginning, well, let's increase the price of my product, and if the product price is higher, then I as a customer have to pay more, which is not good for me, which reduces my consumer wealth, and it's detrimental to my wealth level. So this is showing you that if we talk about tax evasion for corporations, there's a trade-off. The higher the payments for a corporation in case of tax evasion may increase the price, and a higher price is bad for the consumers. So in the end, there should be a kind of balance between the tax evasion, the punishment for corporations in case of tax evasion, and the negative effect a higher price has on the consumer. So you see, if we move on to reality, the problem of tax evasion is more complex. And finally, there's another problem we have to consider if we move up to reality. There is the so-called Ramsey rule you may have heard about if you have already studied the tax system. And the Ramsey rule is telling you a simple message. Have higher taxes on inelastic goods, goods you always need on an everyday basis, like food, for instance. And lower taxes on so-called elastic goods. Elastic goods are luxury goods. Why does the Ramsey rule is telling us this? Well, if you have high taxes on inelastic goods like food, you cannot bypass this. You always need this, and there's no way to go around this. And therefore, tax evasion is quite difficult. You need food, and if you have to pay a high tax on these items, well, you pay it anyway. On luxury goods, well, you can say, well, I don't consume luxury goods, and therefore, from an economic efficiency perspective, you should have, according to the Ramsey rule, lower taxes on these items. This is the Ramsey rule. But if we study now tax evasion, we can show that the simple Ramsey rule, the simple message, is not true. So in case of tax evasion, it definitely makes sense to have higher taxes on luxury goods, on elastic goods, and lower taxes on inelastic goods. So what you have learned in the beginning of a lecture in public economics, the Ramsey rule, may be not true in case of tax evasion. I hope you have learned now something about tax evasion and how an economist would approach this problem of tax evasion. We have seen that the probability and the fine you have to pay both have a huge impact on the evaded taxes. And if you increase the probability, if you increase the fine, tax evasion should go down and should be mitigated. If you're interested now in tax evasion from a business ethics perspective, take a look to the class of my colleague. And in the end, we bring together both perspectives. Have a nice day. Bye-bye. Audio Jungle.